This video is meant to be a review of factoring, the different kinds of factoring that we can come up against. It's not meant to be an introductory lesson on factoring. I'm just going to be reminding you of the different types of factoring that you have in your repertoire. We'll be talking about common factoring, factoring by grouping, difference of squares, as well as factoring simple trinomials and then complex or trickier trinomials. Now, in terms of trinomial factoring, there are a number of different techniques that you can use to factor trinomials. I am going to be reviewing the technique that I think works fastest when you have good math skills in terms of being able to know your multiplication tables quickly. It's not a step by step, it's just playing with the numbers to figure out what values work to create the two factors. There are more stepwise methods. Decomposition is one. An Australian method is another. There's a box method of finding your factors. And if you're looking for a more stepwise method, then this will not be the video for you in terms of trinomial factoring, but please watch how I play with those factors to come up with the different values that, that do complete our factoring of our trinomials. So let's take a look at common factoring. Common factoring is using the distributive property in reverse. So instead of multiplying a constant into a factor or a binomial, or perhaps a larger polynomial, you must look for the greatest common factor, often given the initials GCF, that divides evenly into or out of all of the terms. When I look at the greatest common factor between 3 and 9, I could divide a 3 out of each of those, and that's exactly what common factoring is. Essentially, you are dividing a 3 out of each of them. You're pulling it out front so that you could distribute it back in later if you really wanted to. And if I divided a 3 out of that first term, I would just be left with my x. If I divide a 3 out of that second term, I am just left with a 3. So common factoring out that greatest common factor. In the next one, we've got something a little bit more complicated. The greatest common factor between these two terms, well, I don't have factors between my coefficients, but this has an x times a y, and here I have 3 x's multiplying by 3 y's, so what could I divide out of each? Well, I could certainly divide that single x out of both of them, and I could divide 2 y's out of both of them. And if I did, and I actually encourage you to show it as a division, and then you don't lose track of what it is that's still staying and what's going out of each of those terms. But if I divide that x and those y, that y squared out of each of those, I am just simply left with a 4 in front here, plus 3, and I will have 2 x's left over and a single y left over for a 4 plus 3 xy combination at the end there. Of this one, my greatest common factor, well, 75 and 18 are both divisible by 3. 5 x's and 3 x's, so I could take 3 out of each of those. 2 y's multiplying and 4 y's multiplying, I could divide 2 of those y's out of there. And so when I divide the 3x cubed y squared out of each of them, I can see that I would have 25 left over with 2 x's left over in my, oops, sorry, I forgot to show it out front. Sorry, we truly do need to show it as a distributive property. So 25 x's would be left over with an x squared. And if I did multiply that back in, I would get exactly where I started, minus. And then I've got 18 divided by 3 is 6. My x's will cancel out, so I've got the same thing over itself with nothing left. Same happened here with my y squared. And then y to the exponent 4 over y to the exponent 2, I would have 2 y's left over. And so there I've taken the greatest common factor out of each of those binomials and done some common factoring. Factoring by grouping, just as it says, some polynomials do not have a common factor for every one of their terms. These polynomials can sometimes be factored by grouping the terms that do have a common factor. And so the theme that happens here is we decide what terms to cluster together that would allow me to common factor something out of just those two terms. And here I could common factor an A out of each of them. For this one, I could common factor a B out of each of them. And this one, I
Have
could
your
common
attention,
factor.
please. Would Gurpreet Randhawa please come to the main office for a message? Gurpreet Randhawa, please come to the main office. Thank you.
Sorry about that. And the common factoring by grouping is only actually useful if, when we look at what we have factored out, we actually get another common factor. In fact, in this term and this term and this term, I have that bracket in common. And so what I'm going to do is divide that bracket out of each of those terms and pull it out front into one position. If I divide the bracket out of this term, I'll just have the A left. If I divide the bracket out of this term, I will just have the B left. And if I divide the bracket out of this term, I will simply have a C left. And so there I've got it fully factored using factoring by grouping. Similarly, in my next one, I'm going to take a peek at grouping those two terms together. In my first two terms, I have a common factor of that 4 could divide out of each of those, as well as x squared could come out of each of those. If I take a 4x squared out of this, I'm left with an x minus, and if I divide the 4 out, I get a 3. Divide the x squareds out, I have nothing left over in terms of a variable set. And now I ask myself, what could I divide out of those last two terms that would leave me with that same common bracket? And the answer is a -1. If I divide a -1 out of each of those pieces, then I will be left with an x, (x) divided by -1, and a 3 divided by -1, I would have a -3. And so there I get the very same bracket. Again, in this collection and this collection, I have the very same bracket that I can now common factor out front. If I do, I common factor the bracket out of this term, leaving me with the 4x squared, common factor the bracket out of this term, leaving me with the -1. Now at this point in time, I want to talk about this factor, because this factor is not fully factored. This is actually what we call a difference of two perfect squares. And so I want to scooch down here to this difference of squares area here and just remind ourselves, when I have two terms separated by a minus, a difference of two terms, if those two terms themselves are perfect squares, a 9 is a perfect square because it's 3 squared. An x squared is a perfect square because it's the x multiplied by itself. So these have a unique factoring in that if I have an x times an x, I will get an x squared. And a 9 would be a 3 times a 3, but in order to get a -9, one of them would have to be a positive and one of them would have to be a negative. And the beauty of this is, if I were to binomial expand this out, foiling it out, I would multiply my x times my x, I would get an x squared. An x times that -3, I would get -3x. A 3 times my x, I would get +3x, and a 3 times that 3 is the -9 we needed. But what's very cool is my middle two terms subtract themselves away. I have 0 x's, and I'm just left with that x squared minus 9. And so a difference of squares is a unique opportunity to factor into two binomial factors with the very same terms, just the opposite sign in between. And that is what I have here. 4x squared is a perfect square, a 2x times a 2x, and a 1 is certainly a perfect square, 1 times 1. And so I have an opportunity to factor this further. 2x times 2x gets me my 4x squared. 1 times 1 certainly gets me my 1, but if I want it to be a -1, I would have a positive and a negative term. My inside, if I were to FOIL just that out, my inside would be a 2x term. My outside expansion would be a -2x. Those would subtract away, leaving me with just the 4x squared minus 1. Finally, if we go back to our common factor, our factoring by grouping, again, if I group these guys together, I do have an opportunity to look for a greatest common factor in those two sets, but what I want to encourage you to do is to always common factor first. It will just make your life way easier in the end. And we do have a common factor in all of our terms. Every one of those terms has an x term. Every one of those terms could have an x divided out. And so I pull that x out front. And
Miss Day, please call 506. Miss Day, call 506. Thank you.
If I divide that x out of each term, divided out of here, I would just be left with an x cubed. Divided out of here, I would have a negative 6x squared. Out of here, 2x minus, and if I divide the x out of there, I'm just left with a constant. Now we have a cubic polynomial that can be factored by grouping. I'll take a look at each of those terms. I'm going to use square brackets to sort of keep these brackets separate. And I look to see, of those two terms, what do I have in common? It is an x squared term. If I divide an x squared out of each of those terms, I am left with x minus 6. And in order for factoring by grouping to actually accomplish factoring fully, we would need to factor the very same value out of each of these terms that would leave me with this same bracket. So that's a 2. Not all trinomials, or sorry, cubics here with 4 terms factor by grouping, but some of the special ones do. And I leave myself with an x minus 6. Now I have that very same bracket in each of these terms. And so what I'm going to do is factor that bracket out front, leaving me with an x squared plus 2. And at that point, I wouldn't need my square brackets anymore. Now this factor here is 2 terms, but it's not a difference. I don't have a difference, and I don't actually have 2 perfect squares, and so I'm finished factoring. I'm fully factored for that particular quartic function. So back to our difference of 2 squares. 8 isn't a square. An x squared is a squared. 18 isn't a square. But remember, always common factor first. Always, always, always. And so if we're always going to common factor first, I can divide a 2 out of each of those and pull it out front. 4x squared minus 9y squared. There's my perfect squares. 4 and 9 are certainly perfect squares. And so this becomes a difference of 2 perfect squares. And so 2x times 2x is the square root of this term, gets me back to my 4x squared, and 3y times 3y gets me to my 9y squared, and if I want it to be a negative 9y squared, one of them's negative and one of them's positive.
Ms. Gingrich, please call 506. Ms. Gingrich, call 506.
This one is a little bit trickier. This one is sometimes hard for students to recognize as a difference of 2 squares, but I have a difference, and I have something squared and something squared. So I do have a perfect square on either side of my difference, and so I truly do have an ability to factor this as a difference of squares. What I'm going to do is set myself up with a opportunity to factor 2 factors, one with plus, one with minus. And how do I get to a 5x plus 2 squared? Well, I would have that same bracket multiplied by itself. So I would have 5x plus 2 times 5x plus 2. That would be my 5x plus 2 squared. And then same deal here. The same bracket times itself would get me to that bracket squared. So x minus 2 and x minus 2. And so I have the very 2 same collections with an addition and subtraction, and then I would just be collecting like terms in my inner bracket here. 5x's plus another x would be 6x. Positive 2 and negative 2, that's going to be 0, so I'm done with that. Over here in this other bracket, remember my distributive property here. I'm subtracting one of these x's and subtracting one of these negative 2's. Please remember that you are distributing a -1 into this bracket, I would encourage you to write this extra step out. I can't tell you the number of times I have seen silly glitchy errors. Students will get quizzes and tests back and they'll go, I knew that, I just forgot to do it. And so if you write it out, you'll never be at a loss for not having it. And so I have my 5x minus my x. I have 2 x's plus another 2 x's for 4 of them. And I have got a fully factored difference of squares there. All right, trinomial factoring. To factor our trinomials, we mentally try to figure out what two numbers multiply to this value here, 12, and yet add to an 8. And so what I do is I don't do a decomposition method, as I said earlier in the preview of this well, sort of. Anyway, this video, x times x is x squared. Now, if I just barreled in and went 3 times 4, 3 times 4 would be a 12. But if I was to expand this out or FOIL it out, my inner term is a 3x and my outer term is a 7x. And that does not make 8 x's combined together. So this is where my mental math facts come into play to know that if I go 2 times 6, those are the two numbers that multiply to a 12 and yet add to an 8 because my inner term is 2x, my outer term is 6x, and if I make them both positive, I not only get a positive 12 out of that multiplication, but a positive 2x and a positive 6x gets me that 8x that I was looking for. Over here, if we have a negative, then I can set myself up here, ask myself, well, how do I get to an x squared? That would have to be x times x. How do I multiply to a 15 yet add to a 16? Well, that would be a 1 times 15. Now here, I need this to be a positive 15, and yet a negative 16. Here I have 1x. Here I have 15 x's. To make it a negative 16, I'd need them both to be negative. And that would be excellent because a -1 times a negative 15 would be my positive 15. I teach my grade 10s to recognize this as my last sign tells me whether my signs are either the same or different. Here my signs are the same, they are both positive. Here my signs are the same, they are both negative. Here my signs are not going to be the same. They're going to be an opposite sign, and the bigger one is going to be the positive, or the one that results in the bigger term if we were to expand it. Now, look, I can common factor. Always, always, always common factor first. I can common factor that 3 out, allowing me to have a much easier trinomial to factor. Always do yourself a favor and watch for common factoring. Now, I simply need to ask myself, how do I get to an x squared? Well, that would be x times x. How do I get to this y squared at the back? Well, that would be y times y. And yet, I need to figure out how to have two coefficients here that would multiply to a 6. Now, it could be a 1 and a 6, or a 6 and a 1. Could be a 2 and a 3, or reverse position. And I just plunk them in. Some opportunity, some combination. I might have to rub it out and change it if it doesn't work out. But I look here and I think, all right, this would be 2yx or xy. And this outside term would be 3 of an x times a y. And if I added them, I'd get 5. But how would I get 1? Well, if this one was positive and this one was negative, I would get a 1. In order for this set to multiply to be a negative, we would have to have a negative here. For this one to be positive, we have a positive here, and that allows me to have my negative times my positive, which gives me my negative 6y. And so my signs are not the same, and the bigger expanded term has to be the positive. Lastly, looking at some trinomials that don't get into complex numbers. That's not what I mean here. It's more trickier numbers. And the only difference I have is my leading coefficient isn't an invisible 1 here. I had 1x squared, factored it out to have 1x squared. And so what I'm going to do here is just look at some possibilities where I don't have just a single x squared. I have 4x squareds at the beginning. And this is where, if you find factoring tough, a stepwise method like decomposition or Australian or the box method or any other method that you've been given a set of logical steps is often quite valuable. I feel that even if you have been taught a set of logical stepwise steps like decomposition, it is very valuable that once you're a good factorer with your logical sequence of steps, start trying to juggle the numbers in this manner. Now, I recognize that there's a number of ways to get to 4x squared. Could be 4x times 1x, could be 2x times 2x. I'm just going to plunk in one combination. I might have to rub it out and try something different later, but I'm just going to plunk in one combination that could possibly get me there. And there's multiple ways I could get to a 15. Could be 1 times 15, 15 times 1. It could be a 3 times a 5. And I just put those numbers in and I check to see whether I'm anywhere near accomplishing a negative 16. I check by checking my inside term would be 6x. My outside term, well, that would be a 10x. And can I make a 16x out of this? Absolutely. And if you want it to be negative 16x, they would both have to be negative. Signs are the same. They're both negative. And so there we go. I didn't even need any stepwise method. I plunked in, I guessed what might be the values, and I found it right away. This one, another tip, if you've got a prime number, there's only one way to make a 3. It's a 1 times a 3. Now I recognize I want that to be a negative 3, but I'll take care of that at the end. And I do know that I can go 1x times 6x, or a 2x times 3x, or a 3x times 2x, or a 6x times 1x. But honestly, there's only 4 possibilities. And so I just start playing with them. Let's try the 2x times 3x. And the reason I'm sort of staying low with my numbers and not trying that 6x is my middle term's not very big. Signs are different. Signs are opposite, and they're both, or the larger FOILed term will be positive. Let's just see. A 3x and a 6x. I am not going to be able to make a 7 out of that. And so I try one of my other 4 possibilities. If it's not 2x times 3x, maybe I'll switch those positions. 3x times 2x checks my inside outside. 2x times 9x, yes, I could make a 7 out of that. If my 2x was negative, in order for the 2x to be negative, this would have to be the negative, and to get a positive 9, there we go. Even though there's multiple possibilities, it didn't take very long to find the one set that allowed me to factor this. Now these numbers are so big, I immediately check for a common factor, and I'm disappointed because it's not there. However, I do have a prime number, this 3, and so what I'll do is I'll cement that 3 first. The only way I'm going to get to a y squared is a y times y. The only way I'm going to get to a 3 is a 1 times 3, and a visible 1, I'll probably not write it. Signs are not the same, and the bigger FOILed term is negative. 12. One of the problems with 12 is that there's all kinds of ways of getting to a 12. 1 times 12, 2 times 6, 3 times 4. But really, truly, that's only 3 possibilities, and even if I had to flip their positions, that's only 6 checks. I'm going to stay away from the 1 times 12 just because multiplying 12 times 3, that gets me pretty big, and my 16 isn't all that big. And so really I'm down to, 2 possible factors, 4 possible positions. It won't take long to check that out. Let's check the 3x times the 4x. Then I have a 4xy and a 9xy. Well, that's either going to add to a 13 or subtract to a 5, and that's not going to cut it to get me to my negative 16. So that wasn't it. So let's try the 2x times the 6x. 2x times 6x gets me my 12x squared. My inside term would be 6xy. My outside term would be 6xy. Now, when I look at that, I want to ask myself, signs are not the same. They need to be opposite here. And a 6 times 6 is getting together to be a 12. And so we're not going to have that as my set of values of factoring. And so let's try to flip those. I could have flipped the 4 times 3 as well. That would have been a legitimate combination. Here I have my 2x and 2xy and 18xy. Signs are going to be different. And in order to make that negative 16, I would have negative 18xy and positive 2x. And I found it with, some inspection work, but a minimum, and it didn't take us very long. I do have a set of problems that I would encourage you to factor with all of our different possibilities for our common factoring, our factoring by grouping, our difference of squares, and our simple trinomials.